Welcome to the Introduction to the Optic API tutorial from MarkLogic University. To follow along with this tutorial, you'll need to download and install MarkLogic. Download the sample data and follow installation instructions by going to github.com/MarkLogicUniversity/MarkLogic9. Download and unarchive or clone the repository. Go to the MarkLogic 9 repository directory, then go to the Data Integration subdirectory. Under Data Integration, go to the Optic API subdirectory and follow the README file for instructions on setting up your environment and next steps to follow. In this tutorial, you will discover what is the Optic API and the benefits of using it. You'll also learn when to use the Optic API and see a demonstration of it. The Optic API blends the relational world with NoSQL document features and performs joins and aggregates over document content. Perform efficient joins and aggregates over your distributed data in the database. MarkLogic pushes many operations down to MarkLogic Database Manager nodes closest to the data. You don't have to transform your data, and you aren't limited to only one view of your data. Combine many Optic API lenses for your data. The Optic API harnesses the full power of MarkLogic's document and search capabilities using a familiar syntax, incorporating common SQL concepts, regardless of the underlying structure of your data. The API can be called from MarkLogic's server-side JavaScript and xQuery, and also from the client side using MarkLogic's REST API, Java Client API, and, soon, MarkLogic's Node.js Client API. Template-driven extraction, abbreviated as TDE, defines a relational and/or semantic lens over NoSQL content. Row templates define which parts of documents make up rows in a view. Semantic templates are useful when data in documents is already stored as semantic triples or would be better expressed as triples from TDE. Both types of views are queryable with the Optic API. For more information on template-driven extraction, see the Using Template-Driven Extraction on-demand video at mlu.marklogic.com/ondemand, and also the documentation at docs.marklogic.com. The plan definition consists of operations on a row set. These operations fall into the following categories. Accessing data. First, data needs to be accessed using one of the lenses available to the Optic API, such as row views, semantic triple views, and lexicon views for range indexes. Row set modification. A plan can filter with where, order by, group things, and also project with select and limit a row set to yield a modified row set. Row set composition. A plan can combine multiple row sets with joins, unions, intersects, or except to yield a single row set. Row set processing. A plan can specify operations to perform on the final row set, including mapping or reducing. Operations on the row set are deferred until the .result method is called. At that time, the actual query is executed. The query is distributed across the MarkLogic cluster, pushing down to MarkLogic Data Manager nodes where possible for more efficient processing. Track events is an example scenario. Races have many runs. Each run occurs on a date, run by a runner. Each runner logs an actual time over the run distance. Races have one runner that is the winner. Given this data, let's say we're a marketing company seeking to build an advertising campaign using this data, and we want to feature a spokesperson that comes from the data itself. Our search is more complicated than just examining rows and columns. Who was the best sprinter? Are these runners consistent in their results over time? Are the features in the personal profiles that might point to them as more appropriate spokespersons than others? In the following examples, we're going to look at data from European football players and teams. The data are stored with each player having an individual player document, in each team having an individual team document. The data may or may not include data regarding player contract information, such as the player's market value and contract expiration date. The player data has an ID field which relates the player to a team and the team to players. We'd like to do some aggregates and document joins over this data, so we decided to use MarkLogic's Optic Api Library. The library is included at the top of the example. op.fromView creates a data access plan from a relational view template. We are creating a plan from a template view with schema called football and a view called players. This will be true for each of the examples. Using the .select method, we are returning names and nationalities of the players. To protect from unknown results that may include millions of players, it's a best practice to limit our results. We've chosen an arbitrary limit of 100 until we have a better idea of our results. .result executes this plan and returns the results in the output window. In this example, again, the access plan is created with op.fromView. Using the .select method, we are returning names and jersey numbers of the players, but only if the player's number is 99. Again, we are initially limiting our results to the first 100. .result executes this plan and returns the results. In this example, we're going to return back player names, jersey numbers, and nationality, where the jersey number is equal to 7 and the nationality is equal to Portuguese. We're going to also sort the results by player name ascending. The op.fromView creates a data access plan. Using the .select method, we're returning names, jersey numbers, and nationality of the players, but only if the player's number is 7 and the player's nationality is Portugal. We're going to sort the results by name, default being ascending. And we're going to, of course, limit our results until we're sure of the amount of data that we're returning. .result executes this plan and returns the results in the output window. In this example, we will find players and team names along with player nationalities. Because the players and teams are stored in different documents, we're going to do a join so the correct team name from the team document is selected for the corresponding player name and nationality that are stored in player documents. Again, op.fromView creates a data access plan. We're doing a join between the player data and the team data. Both contain team ID values. The select method returns the player names, nationalities, and the player's team name. Initially, we'll limit the results to the first 100. .result executes this plan and returns the results in the output window. In this final example, we want to find out how many players each team has currently. We are aggregating the number of players and returning that count in descending order grouped by team name. The op.fromView creates a data access plan, both for the players and also for the teams. We are doing another join between the player data and the team data based on the team ID. We're grouping the row set by the team name, the number of players on that team, and each player's name. The result will be sorted by the total player count descending. .result executes this plan and returns the results in the output window. The Optic API Library adds another dimension of search over document data. It's not a new language, but extends the existing MarkLogic server-side APIs, making it possible to perform powerful NoSQL joins and aggregates across documents. Developers can use document search to retrieve rows projected from documents, join documents as columns within rows, and construct document structures dynamically, all performed efficiently within the database and accessed programmatically from your application. MarkLogic's JSearch and low-level CTS functions target data discovery, fuzzy text matching, and searches where document relevance to the particular search is needed. SQL searches can do document joins, aggregates, and summarize large data sets, as would the Optic API. The Optic API has the advantage of business logic, constructing queries that may include data from JavaScript or XQuery variables at the database rather than constructing desired SQL queries based on retrieved data at the client side and then resubmitting to the database. Sparkle searches can relate data to other facts and infer relationships, even if the relation isn't specifically stated. For example, in our runner spokesperson search, what if we wanted to search for spokespeople in specific regions of Europe, but our data for the races only include the cities where each race was run? We could use semantic data to locate countries based upon the known cities. We could even include searches for other facts regarding those cities and countries that, combined with our document profiles of each runner, might better narrow our search for the perfect spokesperson. To learn more about the Optic API, visit docs.marklogic.com. See the Application Developer's Guide. Look for the section titled Optic API for Relational Operations. In this episode, you learned what is the Optic API, discovered its benefits, learned when to use the Optic API, and viewed the demonstration of the Optic API. To get MarkLogic, download from developer.marklogic.com. The examples from this episode are available from MarkLogic University's GitHub repository at github.com/MarkLogicUniversity. Get more training by visiting marklogic.com/training. Also, a complete selection of on-demand topics is available at mlu.marklogic.com/ondemand. Or download the MarkLogic mobile app, available on both the Apple App Store and Google Play. And don't forget to show off what you've learned. Add MarkLogic as a skill on your LinkedIn profile today. Thank you for watching this MarkLogic University On Demand tutorial.